In this last problem, we're looking at gravity. And gravity is not something that we're going to look at a lot, but the derivation of velocity and distance and time from the forces equals ma is really important for this problem. Okay, we're given that these are two steel balls that are connected to each other only through gravity. So the free body diagrams on this will be just one force, and that will be going towards each other. And I split this problem in half so that this one side is 0.5 meters and this other side is 0.5 meters. When the balls are in contact with each other, there is still a value for x if this is positive x and this is positive x. There's still a value for x because the distance is taken from this center point here. If you want to, you could consider x being from the center point to here. But, and that can simplify your integration equation, but I'm just going to leave it at 5. We're given that these steel balls are steel, so we can calculate the mass from the density and the volume, and that information can be found in your textbook. So let's go ahead and solve for that, where mass equals rho times v, and the density in kilograms per meter And since we know that we're dealing with gravity and we're calculating gravity and it's not just the gravity of Earth, we'll use the gravitational constant, which is 6.673 e to the negative 3. And the equation for gravity is that gravitational constant times mass squared over the distance squared. And this is the equation that we'll use to calculate. The velocity. And we'll solve for the velocity from F equals ma because we can convert acceleration as a function of distance and velocity. And like I've done before, I am going to separate this column where one side we put all the forces and the other side we deal all with motion. So for the left side, we have that gravity equation where we put in these values, and that equals mass times acceleration. And from before the substitution, we also know that this equals v dv dx. And now we can use this as a function of x in terms of velocity. We can cancel this out and simplify it, and then we'll move these to separate sides with their variables. We'll take out gm over 4 and take it from 0.5 to 0.05 over 1 over x squared dx equals 0 to the final velocity. And I have 0 here because they told us that the balls are at rest in their initial position. So integrating this, we'll get negative g m over 4, negative 1 over x, 0.5, 0.5, and 1/2 v squared. If we move this to the other side, pass this to these individual parts, we can solve for it using v over the square root of gm times, and these are substituted in, 1 minus 1 over 1. Then plugging in the values of the gravitational constant, negative 11, and that mass that we found using density, we can solve for the velocity at that final position, and that'll be 4.76 e to the negative 5 meters per second. So it's going very slow, but that's expected for gravity. Now that we've found velocity, we can solve for time. But let's take a step back because we're going to end up with this integration instead of that final position, so that we can then solve for time. So we'll rewrite this integration as negative mg over 4, and like I said, we're going to integrate in that final position, but everything else is the same. So still starting from rest, and integrating it, we get negative g m 1 over 2x minus 1, and I have simplified it just a little bit, and it equals v. And what we know from v is that equals dx dt. And separate these to their sides. And we'll get g m from 0 to t dt equals, and we are going to move this and make it easier to integrate by multiplying by x over x. So then we get that 1 over 2 minus x over x, and that is easy to integrate. And square root of x, 1 over 2 minus x, so we flipped it and moved it to the other side, dx, and this is from 0.5 to x. Integrating the side is very easy. You just get that g m times t. Then integrating this side, I suggest using a calculator. You're probably not going to have something this complicated on a test. So use MATLAB, Mathematica, Wolfram Alpha, whatever you feel like using. Now we're going to put these values in here and here. And we can solve for t, plug in those values as 5, and then you get that t equals 48,800 seconds. And this is the magnitude of time. So this integration is the most important part of this problem, I think. Also understanding just conceptually what gravity is between Earth. But the integration is helpful because you can go from F equals ma, converting this to a function of velocity and distance. And then you can do that once again and turn this velocity equation into x of t.